Field-programmable gate arrays are chips which can be programmed after they are manufactured. But creating the configuration files to program them was difficult. Jason Cong, who has spent his entire career in integrated circuit design, developed ways to address this. Cong worked to map logic into the lookup tables that power FPGAs. He and his students showed how to solve the problem exactly in polynomial time, a major breakthrough. This led to the technology's adoption for all FPGA synthesis tools. He advanced the technology further with HLS, high-level synthesis.
Around 2002, we started a research program, so-called high-level synthesis, where you can just write C programs most of the software people are familiar with. We can synthesize that automatically to the VLSI circuits.
Programming with HLS tools with C, C++ led to Autopilot, soon to become AutoESL, acquired by Xilinx in 2011, ultimately resulting in the AMD Xilinx high-level synthesis methods used today.
But there's also a lot more domain experts out there. They are not necessarily computer scientists, but they use a lot of computing capabilities.
Cong and his group then focused on customizable, domain-specific computing to apply FPGA-based high-level synthesis to a host of different areas. In deep learning for medical imaging, for example, he achieved vastly improved energy efficiencies as compared to conventional approaches.
This is actually the part I enjoy most of doing research. The process is full of surprises as you go.
In the spirit of Chuck Thacker, the breakthroughs of Jason Cong expanded the possibilities for FPGA systems and greatly expanded the scope of customizable computing.
Okay, so please join me to welcome Professor Jason Cong to give the 2025 ACM Thacker, what's that? Breakthrough lecture. Yeah, thank you.
Great, thank you.
Wow, for someone coming from a movie capital, Los Angeles, this feels like the Oscar introduction. I like to take the next 40 minutes to tell you something that we have been doing at the intersection of deep learning and the chip design. So first, I want to say a few words about Chuck Thacker. He's a true innovator, pioneer, and a thought leader. If you look at the 2009 Turing Award citation, he was credited for the invention of personal computers. For many people, that one contribution alone is enough to get your Turing Award, but he also is the co-inventor of Ethernet and many other contributions. I'm very honored and humbled to receive the ACM Breakthrough Award named after Chuck. In fact, I was an intern at Xerox PARC back in 1987. I did not use his original auto computer, but I would use the Dandelion and Dorado, those personal workstations, state of art, way before that's available widely in industry. And over the year, he and I also had multiple discussions on FPGA customized computing. So it's a great loss that Chuck is no longer with us. Also, I'd like to thank KDD for hosting this breakthrough lecture. By the way, every awardee is asked to give a breakthrough lecture. I have to say KDD is now my home community. I'm more in electronic design automation, computer architecture. But this talk is motivated by my interaction and collaboration with many of the researchers in the KDD community, and Professor Jianwei Han, and you saw Jian here before that. Of course, my wonderful colleagues, Wei and Yizhou. In fact, a number of topics I covered in this lecture is collaborative work with Yizhou. But more importantly, I think there's a lot of shared interests between the deep learning and the chip design automation. First, I want to say that we use common tools. For example, graph is heavily used because circuits is equivalent to graphs, hierarchy and space-time trade-off, and so on and so forth. So I was very glad to see my good friend George getting the Innovation Award. George and I was all in that working on large-scale circuit partitioning back in the 1990s. So definitely there's a close interaction between two communities. And I think we share common goals. In particular, and I think we care about the efficiency. In fact, later on I want to introduce this concept called the EGI, the efficient general intelligence. And there's plenty of opportunity under that umbrella for cross-fertilization, chip for AI acceleration, and also AI for chip designs. So let me give you some examples about the common tools we use. I also took an opportunity to explain a little bit of what's in the video. The video highlighted this FPGA's field-programmable gate array. So what is it? It's actually a chip that you can buy, and it's in the office on your desk. You can customize different kind of circuits of your particular applications. They say, how do you do it? The fact is that they can implement any K input Boolean functions with one of those squares. So that sounds quite magical, but it's actually very simple. You just need to store the truth table of that Boolean functions. So you basically has millions of these lookup tables there. So that's really the fastest way to go to a customized chip. You may say, I don't have that in my office on my desk, but that's very easy. You can go to Amazon. They have F1 Cloud, F2 Cloud. You pay something like $1 a minute. You can use that. I teach my class on CS133 that all the students go there. In 2 weeks, they design a CN accelerator in Amazon Cloud. But we don't design circuits using this K input lookup tables. We design circuits using AND gates, OR gates, and so on and so forth. So how do you convert that into a network of lookup tables? In fact, the problem is actually quite simple. The problem, if you formulate in the graph theory point of view, is that you want to cover this graph with K input clusters. And what do you care? You care minimum number of clusters, you care minimum depths of the clusters. For circuit to operate fast, we care about the depths. So that's a well-defined problem. I'm sure a lot of you can take out a pen and pencil paper and start working on it. But that's the problem we solved back in 1992. We showed there's a polynomial time algorithm give you a optimal solution, which was a surprising result because a lot of people were using heuristic at that time. So this goes power all the FPGA synthesis tool today. So very clean graph problems. The second problem I mentioned in the video is that the high-level synthesis. So now you can write a piece of a C program, we can turn it into a chip. So that's quite magical. How do you do that? A key step is scheduling, because you know when we write C, C++, or same thing as PyTorch, right? We don't care about the cycle-accurate execution. So there's no concept of timing. So we need to convert on-time model to a timed model. So a key step of that is called the scheduling. So you have a data flow diagram, and then you got to convert it step by step into a cycle-accurate diagram to say what computations carry out at what step. So that actually, we solve it again optimally, that it's a little bit of relaxation on the area constraints, that so you can formulate it by a system of difference constraints equations. Again, that's what will be a graph problem you enjoy to work on. I'll come back to this problem later on. So that's first thing we have in common. So we love graphs. I see many graph-related sessions in KDD. The second thing is that we care about efficiency. In my opinion, that we'll get to AGI sooner or later because so many people are working on it, and also the definition, to be honest, is quite vague. I do not know when we'll get there, but we'll get there sooner or later. I think what matters most is the efficient general intelligence. So I use this term EGI. And just give you some sense that if you want to serve a DeepSeek R1 model, that you need 32 H200 GPUs at 11 kilowatts. And so if you run it for 12 hours, so that's 500 megajoule. That takes like 4 days of power consumption, energy consumption of an average US household. So that has eliminated applications. I don't want a rack of GPUs running around in my kitchen to do some intelligent work, right? In comparison, human brains, we have about 86 billion neurons operating at the 12 to 20 watts. In fact, that when I told this to a neuroscientist at Stanford last weekend, he corrected me. He says, yeah, we have about 80 billion neurons, but only among them, about 16 billions is doing intelligence. The others really motor control and other things. So 20% of neurons is responsible for intelligence. And so if you run that for 12 hours, and it's basically can be powered by 2 bananas, right? So that's the contrast. But that's just for the intelligence part. You probably also want to move around, do some physical activity, so don't just eat 2 bananas for a day. So that's actually, so let's see that how that contracts with some the LLMs we have. We says, what about we just shrink the LLM size? Maybe that's a lot more efficient. So I asked students to do a kind of a pick a task. He picked up the task, reading a paper. He says the average paper has about 7,000 words and like 18,000 tokens. He says human can read it in 30 minutes and at about 1.2 joule per token. But that must be a very good student to read a paper in 30 minutes. You let the DeepSeek read it, and it's very fast, 30 seconds. And so that's, remember, 11 kilowatts. So that's about 18 joule per token. We also tried the Llama 3, it's an open source model, and so it's 20-some seconds, and 5.6 kilowatts is more efficient, and so that's 7.3 joule per token. And if you shrink it to Llama 3 billion model, that's much smaller. So that's 0.4 joule per token. First, I was impressed. I said, wow, that's actually even more efficient than human, right? However, if you look at the qualitative result on the right-hand side, you can have all sorts of scores. Here, we did not use PPL. We use a summarization score, I think. So that drops from 25 to 20. So that's more than 20% drop. So that's probably not acceptable. So we do want the efficient model with also high quality. So how do we improve the efficiency? So the key to LLM efficiency, I think everyone in this audience probably knows, is the context window. How long the context we keep to do the attention, because the attention is the key and that grows quadratically, right? And you may say, we can reduce attention very drastically all the way down to 1. So what is that? That's state space models, right? However, if you run state space models, we also did experiments, and for small lengths, it works well, but for larger lengths, the contact lengths, input, the quality drop significantly. So, so we have to find something to compensate that loss. So how can we learn from future? How does our brain handle this? I will say that we have, so that's where we introduced the concept of hierarchical memory transformer. When you see an old friend that from last year's KDD, you are not going to do attention to everything happens in the last 12 months. You are just going to do attention to what happened in the last KDD, that 1 week of a period, right? So basically, we want to mimic the human capability. Now our memory has hierarchies. We have sensory memory that you hear and see me on the stage. We form short-term memory when we have a conversation at the coffee break and after that at the lunch. And then we form long-term memory. We put it aside after we sleep. And the next time when you see me again, maybe 12 months later, and then you will recall that long-term memory. We do not have that long-term memory capability in LLMs and the recording capability. So that's where we introduced this concept called the HMT, where the first thing is that you can start with any backbone model like Llama, DeepSeek, whatever. And the first thing is that let's assuming information flows this way from right to left. And for the current segments I'm processing at this moment of time, I want to call the LLM to figure out what topic I'm discussing or what's the scenario. For example, we are at KDD, and then immediately I have do cross attention to everything I have in the long-term memory, pick up one or multiple episodes which are most related. And so those episodes will come in to as the input to the backbone model with the current segments, maybe with the segment from yesterday. So that immediate the past and together with the long-term memory will form the output. So that's where the efficient comes in. I'm not doing attention in the everything happened in the last 12 months, only to the ones in the last KDD. Moreover, now it forms a new episode. That episode is going to be put in the long-term memory. So you say, okay, how many can you put it there? It's actually quite amazing that even you just put in, or in the on-chip memory, you can put in the order of thousands of tokens. So we can basically attend equivalent to a contact length of about millions of tokens we can deal with. If we can put it into HBM, which is off-chip, so then we can put in millions of these long-term memories, and we can have billions of links. If we put it into SSD, so that's terabyte of data, right? So it's basically unlimited. All the things you ever read, ever seen, that I can attend to. So with that, that's the one we're going to implement on silicon. Not the R1 model, the Llama model, but something a lot more efficient. So just give you some sense is that when the GPT-2 3.5 came out, that's about 20 billion models. We can start with open source 3 billion models from Llama, and then we add HMT, then we get comparable, even better scores, but that's with 708x reduction in memory size and big reduction on power consumption as well. You can shrink it even further compared to 7 billion chat models. We can actually use 350 million the OPT models with hierarchical memory transformer, and then we get a 20x reduction and then 3 or 4x reduction in energy. So to us, this is almost like another DeepSeek moment. So the message is that long-term memory helps a lot. So now I put this in the table, hey, we are much better that we are getting back to the 300 or 400 billion Llama models, right? But then we are with that much lower energy efficient, the energy scores about actually less than 8x of human assumption. So you may say, hey, what about the gap to the DeepSeek? DeepSeek has a better score, but in order to do that, you have to distill DeepSeek into a smaller model. The nice part with HMT is that it's a plug-in, it's an add-on to any backbone models. So in fact, when we did this work, DeepSeek did not come out, so we used the Llama model. Now DeepSeek is out there. We could actually use a smaller model from DeepSeek to do the same experiments. In fact, any one of you can do that. And so my students are also looking at the latest Q1 models, because this is all open source that you can download it in the Hugging Face and try it yourself. So with this, we are going to take it to silicon, so to further improve the efficiency. So the good news is that if you go to silicon, that the HMT part, the hierarchical recall memory and long-term memory, all those part is very efficient, less than 5% of the area on the left up corner. So it's not totally proportional. If I draw it so small, you will not be able to see it. So that part is very efficient, very easy, and also go very high speed. It only adds about 1% of a latency. And as I said, it's very flexible. You can give me another backbone models we can integrate to get this hierarchical memory transformer. The challenge, however, is the backbone. Actually, the video shows that we did the first neural network, deep neural network acceleration, that the AlexNet, in fact, when it came out, that's more than 10 years ago. And I told you, right, FPGA is the fastest way to silicon. So we published result early 2015. It's like 1 or 2 years ahead of Google's TPU. Coming to Llama models or any of these large language models is very challenging. And first, your number of parameters most likely increased by a factor of 50 to 100. And also the flops, the amount of computation from gigaflops to teraflops. So that's 1,000x increase. And also the on-chip memory, it's significant. But we still have the same demand of the latency. For example, image, we can do about 20 milliseconds per image. And here we want to do basically 10 to 20 milliseconds per token, right? So that in the seconds I can create hundreds of tokens. So we want that kind of efficiency that in speed and also in memory usage. How do we do that? In fact, we use a number of techniques, but for this audience, I just want to share one technique and also need your help, is quantization. So you take a model, you want to actually reduce the bit width. That can be very effective. For example, you're starting from a floating point 32-bit, and we go through a systolic array, we get the result. So that's where you do the weight and the generation, tension generation, all these things. I will come back to tell you about systolic array later on, but for the time being, you remember this is like basically the engine in a TPU. So you can say, I will shrink that from 32-bit to 4-bit. I put it into systolic array, and then I will actually dequantize this, give you 32-bit afterwards. So if you do that, you can see that there's some problems with the animation, small problem. So 18% of resource usage now is down to 5%. That's great. However, if you go back to see that I have a PPL score about 9, and then that, is a problem that increased to 70 or 80, right? So that's clearly not acceptable. So simple quantization is not going to keep the quality. So how do we do that? So we were looking around, we really like this paper from Meta called the spin quant. So the reason we cannot do simple quantization is that most of the things you can quantize, but in large language models, they always have a few channels that's called outliers. They give you very large errors if you do quantization. So it's data dependent, you cannot predict that ahead of time. So the spin quant idea is very clever. It says, the data comes in, I will do a rotation. In fact, they had the Hadamard matrix to do a rotation. And after that rotation, things got smoothed out, then I can do quantization. So for that reason, so we add a module to do the rotation, and there's a rotation matrix, right, with your input. And then everything is rotated, and the systolic array will compute the rotated input with my weights. The weights will be rotated accordingly to give you equivalent result. And you can go through multiple layers, and finally the last layer is rotated back. So I have the inverse of that matrix, rotation matrix. So with that, actually, we get a much better result. The PPL dropped from 76 down to 12. By the way, there's still a gap from 9 to 12. So that's where I ask your help, is that maybe some of you will get in and give us even better algorithms, right? My team is also working on that to see what other ways. And in fact, our goal is to go not only stop at 3 bits or 4 bits, we want to go less than 1 bit. We are having an active project with Microsoft on that, right? You may say, why it's even possible? It is possible if you think about it, if you can do some clever encoding of that. So with that, this is an active ongoing project. We can take Llama 3 spin quant and with hierarchical memory, and we can put it on a single FPGA, right? So this is actually the throughput and the areas all it takes. And so basically, remember reading a paper, we can get it down to less than a minute. And then also we can give you this, the throughput in tens to hundreds of tokens. And so students are actively putting it into a newer FPGA at the 7 nanometer, so we can get a 2x improvement in efficiency. So what's the implication? So now you can look at this table again. We come down to a smaller model and with hardware implementation. So now we can be 10x less than the human energy for this specific task for language processing. And there's a lot of interest that our industry partners also says, can you do it with video, with image, and so on and so forth. So I'd be happy to see some of you in this audience to take on that task as well. So you may say, wow, this is your lab. We cannot do that. In fact, our goal is to really make everyone to be able to design customized accelerators. But before I go, I want to see a show of hand. How many of you had designed some circuits one way or another in this KDD conference? Oh, it's not bad. I see a few hands up there. So that's very encouraging. But don't feel bad if you cannot do it, because not too many, the way I see it. I went to the US Bureau of Labor Statistics, and you look at the numbers. There are about 2 million people says they are software developers. They make a living by writing softwares. There are less than 100,000 people that claim they are hardware designer. I cannot find a category says chip designer, so I think this is the closest I can get. I believe among these people, maybe a fraction can design chips. So the ratio is like a 20-to-1, 30-to-1, similar to the show of hands here that I don't see many hands up, right? So my goal that our research program in the last decade was to enable the interested software programmers to do chip designs. So in fact, I wrote this article in the CACM back 2 or 3 years ago called Democratize Domain-Specific Computing. Domain-specific computing means you will design your own chip for your own problems, right? So when I say interested, there's a section of the software programmer they're interested in performance, right? They will do some optimization, try to do that. There's also other programs just put up a web page and all these. They probably don't care about the performance. The reason you have to do that, you have to remember linear scaling has stopped. You don't get automatic performance improvement, and the end of a Moore's law scaling is probably within sight. So when I was a graduate student, the life was easy. You write a program, you don't do anything. After 2 years, performance doubles. After another 2 years, performance redoubled. So it's a fantastic period. But now you have to do some hard work, including designing circuits. So the good news is that it's actually not that difficult with the tool we created from your software program to a circuit. So I showed you this very simple procedure. This is a matrix vector operation, which is actually very important for you to get all these Q matrix and the query and the key generated, right? So that you can get a chip to do that. So you says that's what's the problem. That sounds solve the problem. However, there's some challenges. The first challenge is that if you just run it without anything, you actually get a design which is 13x slower than CPU. Not what you want to do acceleration. However, you just need to put in 3 pragmas. Pragma stands for hints to the program. You says, this loop, I want to do pipeline. This loop, I want to do parallelization. And the inner loop, I want to do parallelization as well. After you put in this 3 the pragmas or hints, it's 130x faster. Okay, so it's a difference between day and night. And the good news is actually you only have 3 different pragmas to put it in. One is pipeline, the other one is parallel, and the third one is tiling, because this design is not very large. You don't have to do tiling. You says, that's not too bad. Let me just try at every places. But that's not going to work, because when you do the compound the computation, in fact, the total configuration, even for this simple design, is over 3 million. Because when you do parallelization, you can take different parameters, parallelize by 8, by 16, by 32, right? So that adds up. So another question is that can we automate this process, that we want to enable software designers without thinking too much to do that. So the easiest approach actually we took is like an expert system-like approach. I gave it to the students. This is quite a number of years ago. The thing about it, if you take this problem as a homework problem, what do? So you start with the program. My advice is that don't do anything. You just synthesize the circuit. Then you figure out what are the candidates, right, where you can do this insertion. And then you look at the report to see where did I spend all my time. Maybe the last loop is where I spend the most of the time. So I will go back to put a parallel pragma or pipeline pragma there. And then you iterate this process, right? So the reason I say is basically I call that the bottleneck-driven optimization, or you can call that the gradient-driven optimization. You look at the gradient where you can reduce the most, you put it in. So this is actually works out quite well. In fact, for industry designs, we can get rid of a lot of a pragma. We can reinsert a lot of a pragmas to get performance. However, remember I talked about that there are 3 million configurations. So if I run this algorithm, and each time I have to call high-level synthesis to get a solution. So that takes about 10 to 30 minutes, depends on how complex your algorithm is. That's too slow, because in a day I can explore about 100, 200 designs. So here now comes a machine learning question. Can you just look at the program with the programmers, give me a prediction, right? That the AlphaGo can do that. Look at the chessboard, white pieces, black pieces, they give you assessment. What's the likelihood to be successful? So we want to do that. And so we want to decide in milliseconds. And this is where we see whether deep learning can help. So I think not only we accelerate deep learning, we want deep learning to help us do chip designs. So with that in mind, so we start building a system with Yizhou's group. So the first step is that we got to create a database. Where do you get data to train, right? But remember, we have that bottleneck-driven system called AutoESL that basically try to get optimal solutions through iterative improvement. Every single one of them is a training example, right? Not only that, because that's actually on the trajectory to basically good solutions, we can also do some perturbation to get nearby solutions. So over the time, we have a database about 80,000, 100,000 designs, which we are sharing with the community. So from there, so we do have data. The second question is, what's the representation? It's very natural to say, let's throw this into ChatGPT, see what happens. This basically, you're saying using a sequence-based representation. But I want to come back, remember that I told you we use a control data flow diagram to represent the circuit to do scheduling, resource allocation. So graph to us is a first-class citizen. So we'll start from this CDFG graph as the baseline representation. Once we have the graph, and then this community, you have all the tools that are available to do the message passing, transformation, and also attention. And eventually graph get turned into a high-dimensional vector. From this vector, will predict both the area and also the performance and also the energy consumption. So that's a standard procedure to do that. With this graph model, the nice part with the graph neural network is very compact. Compared to large language models, you have tens of millions of parameters or maybe 100 millions of parameters, but not in the order of billions of parameters. So we can run it in milliseconds. So we can traverse the design space very quickly, and we pick the top M designs. These are the predicted designs. We run a high-level synthesis tool. That each run is more real, takes 10, 20 minutes, so we can get the exact solution. On the way, we can also compare, did I predict correctly? Did I make a mistake? If I made a mistake, I put it back into the database, and our database is also growing. After we try the small examples, but however, there's one problem is that, I don't know whether some of you experienced that. Many of you use graph neural network initially for social networks. Social network has a property is being shallow. They have the small world property, right? You and I, we haven't seen each other, but the most likely we can get connected through 4 or 5 other friends. And program graphs are deep. You can declare a variable and use it up to 200 statements, right? So how do you do that? One way is that you just add many CNN layers, but you also have the problem of over smoothing. So the way we handle that is that we use hierarchy, because you don't write flat programs, you write hierarchical programs. You have a statement, you have loops, that's one level hierarchy. Maybe you have nested loops, another hierarchy, and then the loops could be in the functions, that's another hierarchy. And then we will propagate the influence, not only in the original control data flow program, we also go through these pseudo nodes that represent the hierarchy. So actually that much faster. You can see the shortest path in the original graph was 25. After we add this hierarchy, for this example, you get down to 5. 5 is good because in our case, the neural network has 6 layers. But we are not ignoring the attention-based model. Definitely that we want to use it is such a powerful tool. So you can have multimodality learning like a Carolyn's representation, the talk right before that. So on one side, we can have a graph representation that gives us encoding. On another side, we can use a sequence-based model, give us another encoding. The easiest way is that you can just concatenate them together, but you can do something that more clever to do cross-modality learning. For example, I can have the graph node, and with especially hierarchical graph node, I can have segments with the program node. We can propagate information to do message passing among them, right, to do cross-attention. So that's one way that to combine different modalities together. You can look at this paper published last year. Another way to combine them together is that the large language models has a very impressive in-context learning capabilities. So we want to make use of that. So we want to basically use a graph encoder and to do the program representation. And then we want to use the attention schemes to predict. So the idea is that I have a whole bunch of examples that, so these are the X-Y pairs, right? X is the graph representation. Y is the, for example, the performance. I've seen many of this, so that's a sequence. Then I give you a new X, that's a new graph representation for a different program or a different configuration. Can you predict the Y for me, right? So that's the way we set it up. Of course, that if you just train it for one application, it's difficult to generalize. So80,000 interesting in this paper we presented about 2 months ago is that first, we have our own training data set. We have this 80,000 to 100, so we make all of use of them. We also generate synthetic data. Large language model is actually good to generate synthetic data. You need some checker to make sure it's not it's still meaningful, right? And these synthetic data, and then we use, for example, also dropout, multi-color dropout to give us a wide range of functions. You want that flexibility so that you do not do overfitting. And on top of that is basically an attention-based model. We call the transformer neural processing. From there, we're also getting good predictive result. Then I have another student come in and says, why do we do prediction? Remember, what's good with LM is to do generation. That is a generative AI age. Can we just generate, optimize the program directly? So in our case, it's actually a simpler problem, right? We have all this program already. We want to generate these programmers. Can we do that automatically? So that's a wonderful idea. But the first, you see there's a problem that the large language model is good to generate token after token at the end. I don't see much work to go back to insert things in the middle of the sequence. So how do we do that? But then actually we come up with clever ways that, to get this value in the middle is difficult. And then you really, what you need to do is that to go back that you have all these variables, then you have a section to set the value to all these variables at the very end. So that becomes a more standard decoder model. You can make use of that, right? And another challenge is that if you change the value from 16 to 32, actually it's a very significant impact. Your circuit size doubles, the performance increased by a factor of 2, but that's a very subtle signal. So the way we handle that is that you have these different programs with different programmers, then we'll get their graph representation. As Carolyn said, you may actually have a small difference that in the original space, but the difference in the latent space can be very large. So in our case, the latent space is the graph representation. So the latent space is things that got amplified, and then we'll take that as a training signal to train the generation possibility, the process. So with that, actually, we are getting very good result that I will just flash this very quickly. Our standard settings to run AutoDSE, that bottleneck-driven approach for 24 hours, see what's the best result we can get. Now with graph, hierarchical graph representation, with multimodality learning, with in context learning, and also in the program generation. So now we can get somewhere between 20% to all the way to 50% improvement. So that's actually better than the baseline heuristic we had. Remember, that was a very decent heuristic that actually got the best paper award in ACM transaction on design automation. So for some of you who are interested in this topic, I will say we do have data sets available. That was actually published in Europe's 2023. We started with 80,000 examples, and now my students have been adding that with different releasable tools. And also remember, I talked about the synthetic examples. So now we have well over 15,000 examples. So if you want to try it, it's very clean data. We have examples and we have labeled result, right? You can see how well can you predict. If you have any problems, send email to Ijo or myself, and we'll get you the pointers to this. But I just want, before I end, I want to say that we should not use machine learning for everything. And the human intelligence is still very important. And in fact, we should make use of that whenever it's possible. Let me show you this kind of a cartoon of how systolic array works that I showed you, mentioned early on. This is actually also basically the engine behind the TPUs from Google. And also, I think, Tesla is using something very similar. So for this, we have a much deeper understanding. How do we do it? So we developed a tool several years ago called AutoESL, Automatic Systolic Array Synthesis. So the key difference is that for structured design, so we know the parameters we're supposed to optimize. For example, the first important step is to do space-time mapping. You figure out what set of loops goes in a spatial dimension, what set of loops goes in time dimension. And so that's one parameter. Another parameter is vectorization, that how many data do I process at the same step, that 4, 8, or 16. So I have a handful of parameters, right? Maybe less than 20. And I don't need 20 million parameters in neural networks or the transformer models. So that's the difference between human intelligence and machine intelligence, because I already know what's the best in the latent space. I did all this analysis already. And so with that in mind, I want to conclude with the outlook, and we're going to take an agentic-based approach. So you give me C program. By the way, we are actively enhancing this. We can support PyTorch, because so many ML people says, we want to start with PyTorch. Okay, so then we go through one agent, which basically does the orchestration. So it's going to mainly do profiling to see, hey, where's the bottleneck and what kind of a computation patterns it has. And for the patterns we can handle by human, like a systolic array. And there's also stencil computation. I didn't talk about in that, run out of time. Basically for image processing, like a CNN, that type of computation, we have optimal algorithm to handle that. We don't need machine learning to figure out what to do. And but then for the rest, I will do some code transformation, make it the most friendly to the high-level synthesis tool. And then I'll do optimization, right? That I call that AutoESL is now our tool. Fin is the tool from AMD, allow you to generate the machine learning accelerators. And I talked about the HARP and the LIFT in early ones for those more kind of ad hoc or the arbitrary designs. So this can be a long list. The agent can call tools, and these are human design tools. And of course, because we did a whole bunch of transformations, we also care about the interface among these tools, and we need to do some tests and verification. So, and then through this process, we can generate more data, and so it's a very positive flywheel and the ecosystem. And at the end, we can generate chips, either in FPGAs or ASIC. I only talk about the FPGA designs. ASIC designs is more expensive, but it can give you another 5x the efficiency to 10x efficiency improvement. By the way, that ASIC chips on the top is something we just tape out. It's an accelerator for SAT algorithm satisfiability. So for many of you who are working on symbolic reasoning and others, think about it. There will be faster algorithms, silicons out there to help you to make decisions very quickly. So with that, I want to conclude, and I want to say there's a lot of things in common between KDD and the chip design automation community. I talk about the graphs, hierarchy, space-time trade-off. And really, we should work on the common goal is the EGI, efficient general intelligence. There's a rich opportunity for across the fertilization chip for AI acceleration, and also AI for chip designs. So I also showed you that carefully engineered AI ML tools can help chip designs. I talk about the GN, ML, LLM, that the multimodal learning. There's a lot of things we did not talk about. I ran out of time. For example, you can do domain transfer. How do you do it? Well, you can actually just do compare, and you don't need to do exact prediction to make progress, and also task transfer learning as well, so on and so forth. But the AI ML is not a replace for human intelligence. It's always important to think about what's the essence about the structured designs that coming that can be very valuable, that the building blocks or maybe the overarching principles of that. So I said the outlook is the multi-agent system to really combine machine and human intelligence. So now our goal is to bring chip design automation to, let's say, KDD community. And in one of you, if you can write PyTorch, and by pressing another button, you can get a piece of silicon there to accelerate your designs. So with that, I will say let's work together, right, to achieve that goal. With that, and I want to acknowledge the funding support from different agencies, and a big shout out to Ijo and her team that are working with us very, very closely that on many of these problems, and this is an effort of a multi-generation of students, postdocs, and collaborators. Thank you very much. Maybe we can take one or two questions. I know this is right before lunch, and people are getting hungry now. Can we go there? Yeah. Yeah, so the question is about connecting HMT with neuroscience and the impact, especially the episode encoding in the hippocampus. And by the way, I want to say I do work with neuroscientists very carefully, very closely, partially also because of the curiosity that to see the connections. Right now, the connection is rather superficial. I will say that we have a long-term memories, and we store different episodes. So that's not a problem. I think what impressed me with the human memory system is that I still couldn't figure out what's the indexing schemes we use. For example, we can access data very quickly, either by time, or by location, or by association. I can just think, okay, give me all the conversation I had with this person, and across different time, different locations. So that is amazing. That I talked to many neuroscientists, there's no clear answer. If we can build the indexing schemes of that specific sophistication, that's actually fantastic. So we have, that's a long story. We have multiple projects going on. We actually help neuroscientists to first to trace all the neurons that, for example, the D1, D2 neuron for motor control that actually has implication of Parkinson's disease. So we are doing that. The other one is that some of the team members build this very fancy camera called the calcium imager. So when you are thinking the calcium concentration changes, we can see which neurons are firing at the real time. So we have an FPGA to do real-time decoding to do that. I think that there's a lot to be learned out of that process. Right.
For the interest of time, may I invite you to come to talk to the speakers during the lunch. And again, thank you very much for the talk. And thank you, Corona, for your great talk. And yeah.